Alright guys, just give me a second. As soon as I started screen sharing, something weird happened. So,
Try it again.
yeah, it should work and give me like one more minute and logging on to my overview.
Made you presenter.
Okay. Oh, are you kidding? Oh, okay. I'll start screen sharing now. Okay, sorry for the delay. Now can you guys see my screen?
Yeah, we can see your screen.
Yeah,
Okay.
you're good.
Yeah, we can see it.
Nice. So today we're going to be learning a bit more about circles, and we're going to learn the area of a circle, learn some basic formulas, and then we're going to go on to some weirder areas, and then we're going to get to inscribed angles if we can get to them. So, starting off from this example, we're going to derive the area of a circle. Did you guys do this last meeting? I don't think so. Did we?
I don't think we got to that point.
Okay, great. So I'm gonna let you guys do this, and you'll see a sort of elementary proof for the area of a circle. So go ahead and look at the steps and try to follow them to find the area of a circle. If you guys are having any trouble, just type it in chat and I'll help you guys.
If you don't know what to do here, try drawing it out. Remember, you can like cut the rings, as long as you're preserving the same area.
Yeah. So, and just to give you guys a more clear picture, I want to, just give you the images of the rings that I'm talking about. So basically what you want to do is take each of the inner rings and try to do something with them. So here's an example of a ring.
You can cut them, bend them, as long as
Yeah.
you preserve the original length of the ring.
So can anyone tell me the shape they get after, messing around with their rings? Just type it in chat. So I'm gonna give you guys another hint, and I think this should be um more more helpful from the previous one potentially. So go ahead and look at one ring and lay it out on its side, and then try to see try to like attach the smaller rings somehow to this shape right here. So you have many rings and try to like maybe stack them on top of each other. Stack them on top of each other to see what you get.
Remember, each consecutive ring, as you move in, it gets smaller and smaller because the radius is decreasing. Let's keep that in mind.
Okay, so does anyone need more time?
Can I have some more time?
Yeah, okay. So I'm gonna give you guys about three more minutes and then I'll go over. So maybe I'll just start drawing something. So maybe if you just attach one other ring, it'll look like this. And if you keep on attaching another ring and keep on doing this, you see like what I've drawn here? Keep on trying to do that. See what you get.
Yeah, think about what shape you'd eventually get, and then how you could find the area of that shape.
Okay, so I'm gonna go ahead over the solution. So, you know, um, what's that? So, you know, right now we're gonna go over an elementary proof. Well, proof in quotes because this isn't a super rigorous proof. You need calculus to do this, or some there is a way to like prove this without calculus, but it's very similar to the ideas. Basically, we can't rigorously prove it with the tools we have right now, but we can create some kind of intuition to find the area of a circle. So, the way we should start is to try to manipulate the circle into something we do know how to do. Remember, this theme keeps on coming up in geometry. You want to be able to manipulate something you don't know into something you do know. So, a good way is to do this is to dissect the circle into rings, right? So just make a bunch of small rings, and if you look at one ring and you lay it on, and let's say you just cut it along its, you just cut the ring somewhere and you lie it across its side, right? And then notice that if you keep on doing this, you're going to get something that sort of looks like this, right? So if you take the most outer ring and you lie it down, well, we know that the outer ring has, a base of, 2 pi r. That's the circumference of the circle. And then that means if you lie it down, the whole base is 2 pi r or pi r. And then if we look at the very next ring, let me highlight this. So basically this ring right here, well, you get the point, corresponds to this ring right here. And then if you look at the second ring, so let's look at this ring. Well, if you cut that ring along the ring, if you just cut the ring and you lie it across the side, well, it's pretty close to the base of the green ring. You see, like, this is the green ring, this is the blue ring, and the blue ring has a slightly smaller, base. Like, you see, these are a bunch of rectangles. The blue ring has a smaller base because, well, the radius of the blue ring's circle is small. So it's going to have a smaller base. And then if you keep on doing this, well, you get something like, if you keep on doing this, and let's say you have an infinite amount of rings, basically this would eventually, you can imagine that the more rings you have, the more close that this shape is to a triangle. So in order to find the area of a triangle, we need 1/2 the base times the height. And we already know the base, right? It's 2 pi r, and take 1/2 of that, that's pi r. But what's the height? And if you see, like, imagine taking this outer ring, like, how do I say it? So imagine cutting all the rings right here, and then lying them like this. Okay, so basically, if you keep on doing this, you'll see that if you take, for example, let me get rid of the colors. Okay. So you take, for example, this ring, and you just, put it on the same, like, y coordinate. You see, this will be over here, right? And similarly, if you take the ring right under that, let me change my color. You take this ring, well, it's right under it as well, right? So, like this, and then I take the one right under that blue ring, is this ring. Well, oh, this is still purple. This is supposed to be purple, but you can see how if you keep on doing this, operation, you have something with a radius r. So that means that the height will have a radius of r. Well, I mean, we'll have a height of r. So our formula for the area of this circle is 1/2 times the base, which is, let me just write it out. So this is just pi r times r, and this is just pi r squared. And I think there is a proof without calculus, and this is already like a somewhat intuitive proof, and I think this is like good enough for you guys now. But Archimedes actually did something that was close to calculus, but he didn't actually use any calculus, and his proof is more rigorous than this. So if you guys are interested in a proof that you guys can still understand but is more rigorous than this, look up Archimedes' proof of circle's area. So here you can just see we arrive at the same answer, and this is our perhaps the most important theorem of circles, is that the area is given by pi r squared. So just to make sure you guys understood everything, I'm going to let you guys go ahead and try this simple example 2.3. If you guys about 1 minute to do this, go ahead.
Just post your answers in chat. This should be pretty simple if you're paying attention.
So I'm going to go ahead and go over this because this is really just an application of a formula. So we're given that the diameter is 12. Well, the diameter is just twice the radius, so the radius is equal to 6. And just look up here, the area must be pi times 6 squared. That's 36 pi. So, rather simplistic example. I'm going to go on to another example, but before we go on to there, some quick terminology. We have, so basically a sector is basically a portion of a circle. Think about a slice of pie, for example, or a slice of cake. You see how it connects 2 points of the circumference and is connected to the center. So a sector is just a portion of a circle. And I think it's a pretty intuitive explanation here. So you see this, the red part is a sector. So now we're going to use properties. We're going to use a sector in the next example. So go ahead and take this one. So you're given a triangle is equilateral with side length 10, and a circle is constructed with center x and radius 10. So it must pass through y and c because they're all 10 units away from x, right? So we want to find the area of sector y, x, and z in the circle. So I'm going to give you guys about 2 to 3 minutes to do this. So if you guys are stuck on this, I'm going to give you guys a diagram, and maybe this will help. Go ahead and label some angles if you're stuck. Okay, so I'm going to go ahead and go over this section now, this example. So technically I don't think we really covered sectors yet, but the good thing about sectors is that they are pretty intuitive. So we basically have that this is an equilateral triangle, and therefore all these angles are 60 degrees, right? So you see that this sector is 60 degrees of the circle. 60 degrees. The sector has an angle of 60 degrees. But also note that in a circle, that there are 360 degrees in a circle, right? So like if I continued this, well, this would be 300 degrees. So the whole thing is 360. And from here, I think it's pretty intuitive that that the sector is 1/6 the area of the circle, and that's because this is 60 degrees of this is 60 degrees of the 360 degrees. So 60 over 360 is just 1/6. So you see how this is like pretty intuitively obvious that this is just 1/6 of the circle. So now we have that this is 1/6 of the circle. So all we really have to do is find the area of the whole circle and then just take 1/6 of that, and then we'll be done. So we're also told that we have equilateral triangle with side length 10. So the radius is 10, and if you remember, the area of a circle is pi r squared. So if you just plug in 10, you get 100 pi. And, well, as I said before, the area of the sector is just 1/6 that. So if I take the area and divide it by 6, you get 50 pi over 3. And if you're looking for some, a harder problem, go ahead and try to find the area of this blue section here. And this is actually quite standard in many geometry problems. You're going to have to not find the area of the whole sector, but a portion of this sector. So go ahead and give that a shot. But for now, we're going to go on to the next problem. And here's just the explanation. And notice that the way we found the area of this sector is very generalizable. And what that means is that we can easily find the area of a sector just given its angle. And you see that this was like, for example, if this had an angle. Let me just generalize it really quick. So let's say you want to find the area of a sector with angle x, right? So let's just this be a sector, and let this have an measure of angle x. Well, we see that this sector is x over 360 of the whole circle. Like, remember, this is 60 and this is 1/6. We just take x and put it over 360. We find what portion of the whole circle this section is. So, well, after this, we just have to multiply it by the area of the whole circle. And therefore, we can just find the area of that sector. So this is the general formula for an area of a sector. So if you put it into more mathematically precise notation, the area of a sector AOB is equal to that angle, this angle over here, which is AOB, angle AOB over 360 times pi r squared. Oh, did someone? Let me share content again. Okay. Oh, was someone accidentally typing?
Yeah, please don't try to share content. It kicks us off, and it takes a while to get back.
Wait, wait. I think someone's keep on sharing their content. I can't share. Someone trolling me? Okay, I think it's back now. Oh, cool. Okay, so now we're gonna go on to a slightly harder problem. You're given that Farmer Tim has 50 feet of fence, and he wants to enclose a semicircular area adjacent to his barn, and he's using his barn as one side of the enclosure. And you're trying to find the area of the space that Farmer Tim can enclose. If you don't really understand that, what that means is basically you have the black line is the side of his barn, and he has 50 feet to put around it. So the blue line has a measure of 50 feet. And you want to find the area of the semicircle. So go ahead and try this. Does anyone need more time?
There's some more time.
Yeah, so I'm going to give you guys about 2 to 3 more minutes to go ahead and try this problem. Okay, so I'm going to go ahead and go over this problem now. So we are given essentially that the blue line here is 50 feet. And, well, a sort of natural thing to do would be to create a circle out of it, right? We're given a semicircle. We know how to deal with circles, so let's just create a circle out of it. Well, if we just flip this over by symmetry, it's pretty obvious that the, this perimeter over here, the one under the already given semicircle, will also have a perimeter of 50. And from that, we know the circumference of the whole circle is 100 feet, but I'll ignore the units for now. So we want to be able to relate the circumference to the area. So a good way to do that is to use the radius, use the formula for radius. And we know that the circumference is 2 pi r, and what we're looking for is pi r squared over 2, right? Because remember, if you find the area of the whole circle, you have to divide that by 2 because we're looking for a semicircle. So we're looking for pi r squared over 2, and we're given that 100 is equal to 2 pi r. And then from here, I think it's pretty clear what we should do. So if you just divide both sides by 2 pi, you're given that 50 over pi equal to r. And now I can just plug it into our other equation right here. We're trying to find the area, and this is just pi over 2 times 50 over pi whole squared. And if you do this, this is 2500 over 2500 pi, 2 pi squared. Did I do that right? Okay, I think I did that right. And then you cancel out the pi's, and you cancel out the 2, and you're given 1200, well, 1250 per pi. So really all this question is about was manipulating the area, the circumference, and relating that to area. So all you have to do is use the formula. So it's a pretty straightforward application here. And now we're going to go to one that's, again, a little bit harder. So I'm going to give you guys the picture for this one. And you're given a man is standing on a lawn wearing a circular sombrero of radius 3 feet. Maybe it's Cinco de Mayo, who knows. Unfortunately, the hat blocks the sunlight so effectively that the grass under it dies instantly. And we're told that if the man walks in a circle of radius 5 feet, we want to find the area of the dead grass. So go ahead and try this problem out.
Just to clarify, he's walking in the center of, well, he's walking along a circle of radius 5, but everything within a 3 feet radius of him is all the grass there is being filled.
Yeah, and this diagram is definitely not to scale, so that shouldn't affect the answer. So.
Anyone have any ideas on how to solve this?
Yep.
Okay, can someone tell me their method of solve? Whoever just spoke, tell me their method of how they solve this. Uh, Whoever spoke, are you there, or do you just want me to do it?
Yeah.
Oh, can you walk us through your method of how you solve this question?
No, I wanted to ask how you did it. I'm stuck.
Oh, okay, my bad. Okay, so a good start for every geometry problem is to always draw out the situation. So here you can see that he's walking in a radius of 5 feet, and fortunately this isn't to scale, but we know that the circular sombrero has a radius of 3 feet. So we're told, essentially, the gray is the dead grass, by the way. We're told that this is 3 feet long. Similarly, this is 3 feet. So now we see that we have almost a circle that we're trying to find, right? The gray area is almost a circle, but an easy way to find it is just to find the area of, like, I'm just drawing a mini diagram. So this is the gray area. So a good way to find this problem is to find the area of the whole circle. Let's subtract the white part inside, right? So, well, we're told that he's walking in a. We're told that this distance right here is 5 feet, and we just connect the other part to the end of this ring. This is also 3 feet because this sombrero has a killing radius of 3 feet. So we see that this whole circle, this like all the way up from the center to the outer ring, that is 8 feet long. So the area of the whole thing, including the white space, is equal to pi r squared. Pi times 8 squared, which is 64 times pi. And, well, now all we have to do is just find the area of the white space. Well, that's just another circle, right? So this circle of radius 5. Oh, wait, my bad. So remember that this is 3 feet long, right? So what that means is this white space right here is 5 minus 3 feet. So this is 2 feet. As I said before, this is definitely not the scale, but you have to remember to subtract this portion right here. That's what we did since the sombrero is 3 feet long, and if you just subtract that, you get this radii is 2 feet long. So the area of the white square is just wait, this is not equal to. I don't know why I wrote equal to, but you get the area of the big circle, big, in the area of the small circle. So small is equal to 2 pi r squared times 2 squared, and this is just 4 for pi. And here, well, remember we're just looking for big circle minus small circle. That's just 64 pi minus 4 pi. That gives us 60 pi. So remember that, geometry problem, good to draw a diagram, and it's if you don't know how to find an area of one shape, try to find that area of the confusing shape in terms of other easier shapes. So you're gonna see that a lot when we get to weirder areas. I think the next one is pretty weird. So go ahead. 2.8 is harder than all the previous ones, but not impossible. You guys are capable of doing this. So go ahead and try this question. So I'm going to go ahead and give you guys the diagram. Ignore X, O, Y for now. I'll talk about those later, but a good way to start is to just draw BA and CE. Those are the parallel lines of length X. And then connect those to center O. And then try to make some guesses about some angles.
So Sahil, the meeting is going to end very soon. So
Okay, so I'm gonna try and go over this problem for the sake of time. If I can't get through it, you guys should read through the explanation. But just looking at this diagram, it seems tempting to say that this is a 90-degree angle, right? It's like almost blindingly obvious, but you have to prove this first. So one thing to note is that okay, well these are all radii, and I connected this to the center O. These are all radii, and
Are we going to rejoin after the meeting ends?
I think we're going to change our schedule, but not for this meeting. No, not for this meeting, but I think that might change in the future.
yeah, we might try that in the future.
Okay.
So we also know that
Wait, so we don't join afterwards?
do not join afterwards.
Yeah, but
Okay.
you can review the there will be the video sent with the handout, and you can review that.
Okay, so you can see here that we have two triangles that are congruent by SSS. So what that means is that the corresponding parts are the same. This is when it's a good idea where we haven't used the fact that there are x units apart. So let's try to use that really quick. So let's just get rid of these right angles. If I draw their altitudes, you'll notice that okay, well, such a congruent triangle by that means their corresponding parts are also same. It means these altitudes are same in length as well. And notice that this makes the distance. This makes the distance x. Like we're told that this is the distance x. And one implicit thing that I didn't really go over is that this indeed is a straight line. Just intuitively, it makes sense because like let this be center O, right? And let this be x. Let's say that we'll do a quick proof by contradiction. If OY is a different line, that means like this, if I continue this, we know since these are parallel, this is 90 degrees. But let's say by proof of contradiction, like this point, let's say P. We're going to try to prove that it's impossible for this to not be a straight line. So essentially, let's say y is here, for example. Let's say y is here. Well, what that means is that we have to change. What that means is essentially we're told that this is a 90-degree angle, and we have to twist it around, right? So what that means is that this cannot be a 90-degree angle. We cannot have a 90-degree angle. So you could do a proof by contradiction here.